Let's have a look at some solutions for fault detection circuit or system. This is your practical activity. If you're watching this video, that means that you did attempt to create all those schematics and diagrams. If you haven't, I would like you to really go through it and do the best you can before you watch this video. This is a test for you. You know how much you know, and how much you can do with your current knowledge. So going through those sections, I'll just have a look briefly through those sections there. We've got block diagram, and you've probably noticed that we've got 3 different fault detectors with 3 alarm relays. Now those relays, they're not relays, they're actually alarm system of relays, or relay logic system, or it could be PLC, it could be anything pretty much. So that's a little bit misleading, alarm relay, because it's not actual relay as such. Then obviously we've got acknowledge button, the sound and flasher unit, which could be incorporated into our system. And you'll see that that's a bigger view, and you can see that the flasher unit is well, it has to pretty much be within the system, unless it's got light incorporated in separately. Now I've assumed that this is in the system, but you can actually, when you're doing your schematics, you can assume that this is actually a unit which flashes separately and it's got nothing to do with lights. So there's a fair bit of interpretation there. And if you go into functional description, you'll see straight away that we've got 2 scenarios. One is when the closed contacts means fault on our sensor, and the other one is when open contacts means fault in our sensor. So depending on the type of sensor, you can use either one or the other. The conditions are very similar. They'll change slightly, but they'll be very similar. And it is up to you to decide, do you want to use closed contacts, open contacts as your fault when you're doing your schematics. Now next, this is an existing schematic which was designed for this project, and that is a disaster pretty much. This doesn't work. You can see that the way it's drawn, it's got positive, negative, so it's almost a ladder diagram except it's horizontal. There would be nothing wrong with it if it wasn't for the fact that actually doesn't work. What's more, not only doesn't work, but R2, if you turn it on, it'll just burn this relay, because the relay itself will be turning on and off. It's powered, turns on, and by turning itself on, it'll turn itself off, and it'll lose power and gain power, and it'll go into this oscillation mode until it burns out. And all the other functions are not working either, so pretty much that schematic is wrong. Now, flasher unit, it is in this schematic, it is actually a separate unit, but it still activates the light, amber light, which means that it's actually just a flasher. It doesn't have its own light built in. So that's what I've assumed, that this is just a flasher similar to your indicator in your car. It's just a blocker unit, you plug it in and it oscillates. And 2 other units, obviously, because this is just one sensor, one module, and you can have multiple modules in parallel. So your first task was to fix that circuit. Now, if you had problems with that circuit, you could actually go into, let's go next section. You can choose one of the scenarios and start fixing it up. You can actually go straight into ladder diagram, create your ladder diagram, and then go back into the schematic and fix it up. I found personally that doing ladder diagram is easier for me. I can actually debug it much easier as a ladder, and then go back into the original schematic and fix it up. Then you can look through optimization, identify redundant relays and contacts, and just reduce number of components. When I do something, I break it down as much as I can. When everything is broken into pieces and as many runs as possible pretty much. Each function or each state has its own run, its own relays and contacts. I look at optimizing it and then just say, well, can I compact it? Can I actually reduce numbers of relays and contacts? So it's a bit of optimization test there. And then you can develop your PLC program from it. So once you've got your relay logic, it's very easy to create your program for PLC, and I'll be showing you all those elements in a minute. And you can simulate it, although I did not find a good PLC simulator which is free. There are some, but you have to sort of look deeper into it. I'll see if I can find some later on. And then we'll look at, oh, you did look, hopefully, at using logic gates. So creating that circuit using logic gates, again, there's a circuit here, given circuit, which unfortunately doesn't work. Again, there's some errors. It's based on wrong principles. There is actually nothing oscillating or locking there. So which means that principally that schematic would never work simply because there is no locking function. There is no interlocking function as such. So let's have a look at some solutions. Now, I've created just one AutoCAD drawing for three different styles. So I've corrected design in the original style schematic. I've created a ladder style circuit, and I've created PLC program logic. Now, you can do it in different files or in the same file. It doesn't really matter. It's up to you. I prefer to put it all in one. And I actually did correct the design, but it didn't look right. Something wasn't quite right there. So I did my ladder style circuit. Then I've tested it. Everything was fine. Went back, created the corrected design, and then went for and create PLC program logic. So let's just have a look at our program. Just go to sheet 1. Okay. Now, when you do things, make sure that every drawing it's in the drawing frame, that you've got your legend, operational notes, how the system operates. I've also included the item quantity and the names of the items. It's a partial BOM. You can create a little bit more comprehensive BOM if you want. You can actually indicate what type of relay stack. Okay, this is SPDT, but how many contacts and some extra information there. So this is the place to put extra information. I'll just go into that mode again. And this is my corrected design. So it is streamlined. It sort of runs like a ladder more. It can be still optimized. For example, you can see R1 here and R1 here. They coming off positive, they're the same, normally closed, which means I could actually run that cable right there, delete this contact, and just use one contact to deliver all the power. So it is not fully optimized yet, but it can be. It's just corrected at this stage. Now, let's have a look. I can describe a little bit of operation of it. So I've assumed that my fault is normally closed. No operation, no fault condition, only white indicator, yes, but it's normally closed. So I've got the circuit for my fault detection, circuit for acknowledge button with its own relay. So I'm using 2 relay system, 2 relays only. Then my 2 lights, normal operation, error, and the hooter, they all have, this is the normal operation is a separate run pretty much, but my light and the hooter are sort of interconnected a little bit, combined. They could be split up again. I could put another R1 contact across there and just create a separate run with amber without hooter at all. So there's a few different things you can do here. It is entirely up to you. There's no correct or incorrect. Actually, no. There are correct and incorrect schematics, but If you decide to optimize it, minimize it, or create more of those contacts, that's all fine. It all depends on how you sort of, what is easier for you and how you feel about it. Now let's have a look at the ladder style circuit. This is where I've sort of optimized it a little bit. You can see that this J1, it's only used once, and then everything splits up into my 3 different runs effectively over here. I can't see how I can optimize it more, but still this is pretty good because the J1 relay, it only uses 3 of the contacts, but J2 uses 5. So it does need quite a few contacts for this operation to be successful. Now, instead of using 5 contacts, I could use another relay, so have J1, J2, and J3, and use those functions slightly differently. But this was my way. You may have alternative solution which also works. PLC program logic, it's taken directly off that ladder style pretty much. The only difference is that, okay, let's have a look at it run by run. Default, nothing unusual, same as this, it's just shown differently. Acknowledge button, yeah, it's the same as this one, no difference there, just shown differently. Then we've got a white light, so again, no difference there. You can see that the symbols are different, but the method is the same pretty much. And then the next 2 runs, which is run 4 and 5, I've got this T on delay, timer on delay. This is basically because in PLCs, flasher is a function. It's not something external, it's something internal. And some PLC programming languages would actually have, you could program it using Visual Basic or some other language, and you can just program that flasher with no extra elements. Just say little box there, flasher, and turn on and off every whatever number of seconds or milliseconds. It's as simple as this. But in generic, I'll just zoom in generic PLC design, if you don't have programming languages to do the flashing, then you can substitute it using timers. And each, it's a timer on delay. You can use actually in that system there, instead of flasher, you could use 2 timer relays or delayed relay timer, sorry, delayed relays, 2 of them, and create a circuit similar to this, which will perform the same function as your flasher. So in this case, I substituted the flasher with 2 timers on delay. So they set at whatever intervals, 1 second, 5 seconds, whatever you want the flashing speed is. Those are internal relays, so they're not external, internal. They don't cost anything. You can put as many as you want. There is a limit, but the limit is pretty high for each PLC. So you're not going to exceed it with a simple program like this. And then basically those timers, 1 timer gets activated, and after the time delay activates a timer which turns this on. This timer gets activated. When it's deactivated, it turns this one on. So they basically activate each other or with the time delay. They click one, another, and they just oscillate between the 2. So that's how that system works. You can design something else. You can assume that, okay, we've got a flasher unit or some sort of oscillating unit as a program, and it can just put a single box and say, on-off flasher program internal. And in a lot of PLCs, you can do that. You don't have to actually use timers. You can actually write a little program in programming language to create that function. Then we've got a light which is activated 2 different ways, which is the same as here. That light is activated either through flasher or directly. So that's what those 2 runs do. And then we've got a hooter which is activated through, and I did duplicate this relay. I didn't want to join it back in. has just created, in this case, I'm using 3 contacts of J1. In this case, I'm using 5 contacts of J1. But those contacts are real contacts. This is real hardware. This is virtual. And there is no PLC which could not handle 10 or 20 contacts. They can handle hundreds. So which means that it doesn't actually cost you anything. You can simplify your program by adding extra contacts in. There's no need to optimize it unless you're working on something which is really big and your PLC does not have enough contacts to so you can utilize them. So that's the program for PLC program logic. And if you have any questions, we can discuss it in the classroom, obviously. So that's it pretty much. This is this task. Now, next is, and I'll just minimize this. Let's have a look at some simulators. So the simulator links are on the web page. This is the simulation I've created for my specific case. And again, if you look at this circuit, it's got this weird element in there. This element is 555 timer, which is a logic chip. Actually, if I go through digital chips. Analog and hybrid chips. Okay, so it's a digital or hybrid. So 555 timer is a chip. It's basically a hardware element, and I did have to put a couple of components around it to make it a flasher. So that element plus this taken resistor, this is just feeding back the output to that input there. 1 meg, this is charging capacitor. Capacitor gives you the timing, so it's an oscillating circuit. Now, by changing this value here, or this value here, you can modify your timing for the actual 555 chip. So, so in this case, I just set some values just so to make it flash. I did have to run this cable there because we need to connect it to the ground. That sort of makes it look a little bit more complex, but now as a flasher, we've got an input to the flasher here, and output from the flasher here, and that's it. The rest of the circuit is I've just created to create this flashing function. The software doesn't have a flasher, doesn't seem to have a flasher, but if you find one, yeah, use the flasher or some other. You can use many different components. You can use logic gates to actually create a flashing circuit. So it's entirely up to you. Now, I'll show you how that works. So if I start running this, you can see the circuit is running, normally closed contact. So in this case, I use normally closed contact as normal operation. I've got 2 relays, a fault relay and acknowledge relay. I've got acknowledge button, and all the contacts are pretty much the same as in my schematic. Now, no fault indicator. So this is my white light. I made it green because, and I used LEDs actually. I made it green because, yeah, you can change colors into different colors, but just I prefer to have a label there and say, okay, this is no fault. Everything else is off. What happens if I activate my fault now? If I activate my fault, then suddenly the header starts making noise and the light starts flashing. So now my flashing circuit starts working. It's flashing. Now, don't worry about those 200 resistors there. They're just resistors because I'm using LEDs and I needed to put some resistors in, otherwise this circuit would not work. Yeah, all the other contacts and the rest of the circuitry works as normal. Light is flashing. So what will happen if I press the acknowledge button? Press the acknowledge, and release it because that's momentary button. And you can see the situation has changed. Now the light is on all the time because the fault is on, but the header is gone. So flashing light is gone, header is gone. This is exactly what we wanted. Now, if I remove the fault, everything reverts back to normal. So those sort of simulators are really good to test simple concepts. If you're doing something really complicated, then obviously it will take you a long time to do it. The software is, it's an online software, it's very slow, but it's actually really good for what it is, you know, for something, for free tool. It's not bad, and you can test simple circuits like this. So I'll just, it gives you a lot of other information as well. You can see, you know, through this resistor, what is the voltage drop, what is the current coming through at any stage. Now that LED is seriously of a part like this. This would burn 52 amps. Obviously I need a resistor there, but I didn't bother in this case putting resistor because this is just a lamp indicator. I assumed that it's got internal resistor. I had to use resistors here simply because that circuit would not work without the load. That resistor gives you load. LED doesn't give you big enough load, and the current would be too big. So that's what it is. I'll reset this. I'll stop it and reset. So whatever you create, test it. Go to the circuit simulator, build your circuit, test it, see how it works. It's actually a really good learning tool. Now let's have a look at our last task, which was using logic gates. And this is another simulator for logic gates. It's really simple, really good, all free. And that circuit there, it uses, okay, I'll just start it. If I start it, white indicator lamp. So the colors, maybe you can choose colors there, but it doesn't really matter. White indicator lamp, so this is all okay. Now, that circuit is built to for an open contact. So no fault means open contact. So it's opposite to what you saw last time. But I'll show you some other versions with normally closed contacts. So this is open contact. When the fault happens, I'll close that contact. Then suddenly horn starts making noise and the light starts flashing. When I press my acknowledge button, then the horn stops making noise and the lamp goes into a solid light. So again, I'll release my fault. No fault condition, everything goes back to normal. So this is how I can use logic gates. And notice that, you know, apart from simple gates, I'm also using SR latches. Now, in those sort of situations where you use logic gates, you need a latch. You need to have stable condition. So without latches, you cannot create that circuit. You must use latches. Now, if you use them this way, or if you create your latch using basic elements, it doesn't really matter. A latch is a latch. You just have to create one. So this is, I'll just stop that circuit. So this is one circuit, normally open. Let's have a look at some other circuits. Now that one is a lot more messy. You can see that you can just connect those directly. This layout is really nice. This layout is not so nice, but it also works. As a testing layout, if you build something like this, yeah, that's okay. As long as it works, as long as you learn something from it, that's all good. So in this case, I used SR latch and D latch, two different types. And the default is, I'll start the circuit. No fault is on, and I'll acknowledge button. Okay, so this is our normal position. Now that circuit works slightly differently because you actually have to press acknowledge to reset everything. So slightly different condition set to this one. So no fault on, white light on, no problem. When we create a fault, then Ember is flashing, Hooter is making noise. When I press acknowledge, Ember goes full light, Hooter stops making noise, and when I toggle it back, it waits for me to press acknowledge button. Now, when I press acknowledge, goes back to normal. So depending on how you want your circuit to be designed, do you want to make sure that you reset acknowledge button works like a reset? So when the fault is gone, you want to manually reset it to normal, or you want this to automatically fault resets itself and automatically goes into normal? So that's a design decision. Sometimes it's a safety decision, depending on the circuit. So it's just different set of conditions, different parameters. So let's have a look at the next one. That one is the same as this one, except it's using just simple gates. Just because it's using simple gates, it doesn't mean it doesn't use latches, because yes, it does. And this is your D latch, those two components. And those four components is a SR latch. Well, actually the other way around. This is SR, this is D. So you can see that you can use basic gates to still create the same environment. Now, when I turn it on, you can see that everything is unstable, goes like crazy. And that's because when you start using just basic logic gates, quite often in the circuitry you have unstable situation and you have to add something to it. It could be pull down resistor, it could be some, there's many different ways of making everything stable, because that's completely unstable. You can see that what's happening there. So what we need to do is, first of all, let's just reset no fault, press acknowledge, create stable condition. So now that stable condition is no fault, white light on. When we create our fault, then Ember is flashing, Hooter is on. When we acknowledge, goes back to Ember solid, no Hooter. When we remove the fault, we have to press acknowledge to reset it back. So pretty much because of those manually built latches, there's stable situations when you power everything on and you have to press at least acknowledge button to really reset it to normal. So I'll do it again. I'll stop the whole circuit. I'll start it. We've got unstable situation. I'll press acknowledge. And now we've got a stable situation. Now I'll reset this, acknowledge again, goes back to white. So everything works. So you can, when you play with the circuit, you're probably going to connect it like this. When you want to make it look nice, you'll go and tidy it up like this. And again, it's entirely up to you if you do normally open or normally closed for fault. It's entirely up to you. Okay, and that's all. I guess I've covered all our solutions. You could also create that whole logic gate simulation using this software. Like this software here is just using logic gates, nothing else. If I scroll down, these are my tools, and you can see that we've got some latches and we've got basic gates, and that's it, pretty much. We don't have too many components here. Now, if you look at this simulator, it does have a lot. It also does have logic gates. So you could create this schematic and simulate it in that circuit or this simulator. It's entirely up to you. Okay, so I think that's it. That's it. If you were unsuccessful in creating working systems, before you watch this video, definitely go back and see if you can fix them, fix your elements, and whatever you've created, test it. Use those simulators, build those circuits, test them, make sure that they actually work. Okay.